Okay, part E, the shape of an ethene molecule. This is just a reminder that a lot of the stuff that's in the first module is sort of foundations of chemistry stuff that can then come up again in any of the subsequent modules, in A2 modules as well, that you'll get onto next year. So shapes is a good example of that. And you explain it in just the same way that, as you would have done in an ABG question. The issue, though, is that in ethene, the shape is this, and of course the complication is that there are two central atoms to talk about rather than just one. But of course the shape is the same around both of them, so you don't really need to worry about that, but you just focus on what's going on around one of those carbons. And remember, the issue with shapes of molecule is repulsion between electron pairs in the outer shell of that atom. So what you need to do is set out what that atom has in its outer shell repelling each other and relate that to the shape that you've got. So what you would say is that that carbon has 3 areas of electron density. Remember, that's a sort of catch-all phrase to include single bonds, double bonds and lone pairs. So 3 areas of electron density, and then spell out what they are, i.e. 1 double bond, 2 single bonds and no lone pairs. And the point is that they are all repelling one another, and that's what determines the shape, because it's the angle which minimises that repulsion that will be the preferred angle around there. And what that angle is 120 degrees, and the shape is called trigonal planar. Okay, and it's the same around both of the carbons, and in fact the whole molecule is planar. So that's all you need for that one. And then we get on to addition polymerization, and it's asking us about E-pent2-ene. So really 2 issues here. First of all, the EZ issue. Remember that alkenes have this possibility of forming stereoisomers. Stereoisomers means that they have the same structural formula in the sense that the bonds are connected up in the same order, but they have a different 3-dimensional arrangement in space. So pent2-ene, sorry, is it pent2-ene? Yes, pent2-ene, you might think immediately of as that. Okay, so 5 carbons with a double bond at the second position. But it could be this. Okay, both of those you can see have the same sequence of bonds, single, double, single, single, but they're different molecules because rotation is impossible around the double bond. That's the key thing. They ask you to explain it, which they don't here, but if they do ask you to explain how you get EZ isomers, you explain that rotation around the double bond is impossible because if it occurred, the pi bond would be broken. That sideways overlap between the p orbitals would cease to exist because you're going here we go. If we've got 2 p orbitals overlap sideways like this, if we rotate round, you can see they don't overlap sideways anymore, so the pi bond is broken. And that's not possible unless you go to very high temperatures, so these therefore exist as separate compounds. If you don't like skeletal formulae, you can draw them out using this kind of way, which is always a good way to draw alkenes out, particularly if you don't like the skeletal formulae. So you would have CH3 at the end, then the double bond, and that one is the Z one, so that will be CH2, CH3 there. Okay, so that's the same as that, and you can see that the important thing is that the hydrogens, there's one here and one here, so they are opposite sides of the line of the double bond there, as they are in this, so those 2 represent the same thing. In this case the 2 hydrogens are up here and here, so they're on the same side of the double bond, and so in this representation they'd again be on the same side like that, and so you'd get that. your more explicit way of drawing it. So either of those would be fine. But in this particular question, it just asked you to draw E pentatwoine. So of course you need to know what the rule is. And the rule is that if the hydrogens are together, excuse me, together on the same side of the double bond, then that's the Z isomer. If they're not together, they're on opposite sides, then that one is the E one, and therefore that at the top is E pentatwoine. Okay, what it's then asking us to do is to say, well, what happens if we polymerize that? So alkene polymers are extremely easy, particularly if you've drawn them out in this kind of way, because the repeat unit of an alkene always, doesn't matter what the alkene is, the repeat unit essentially has that structure where these two carbons are those two carbons. Okay, so that should be your starting point for drawing a repeat unit, regardless of what the starting alkene is. And then the four things that go there, 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 and there are the four things that go there, 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 and there. So that makes it even easier. Okay, and you just say, right, that is my repeat unit. Okay, and if you just learn that recipe, it's an incredibly simple recipe. You can't really go wrong with alkene polymers. But again, you've got to read the question carefully, because it asks not just for one repeat unit, but for two. So you just join two of those together. So make that bond a bit longer, just so there's room for sticking them in there. And you get this. You can put brackets around them if you want, but you don't have to. What you don't want to do is put N's in there. Okay, N only comes in there when you're writing the formula of the whole polymer. It's that repeat unit N times. But if it's just asking for one or two or whatever repeat units, you don't put the N in there. So that's it. Polymers are easy. Don't tell yourself they're difficult. They're not. You just need to practice them. And that's it for question 1.